In your notes regarding simple harmonic motion, okay? Simple harmonic motion, once again, is a system, and we have a particle that's undergoing this system, like a pulled spring or something like that. So, when you're at your starting point, you're undergoing a sine wave, which is in orange, okay? Now, the generic formula for this is the only formula that's given to you on page 54 of your notes is that the x value, the displacement value, equals sine A sine omega t plus alpha. Okay? That's what we're trying to work with. Alright? Now, you basically, one last thing. Okay, so, what we have is this function here. Now, if I change this to a t, and I change this to a t, okay, and I change this to an x and this to an x, so basically it's x equals cos 2t. Can anybody tell me the omega value? The omega value is what? Sorry? The omega value, instead of what comes in front of the t? 2. The omega value is 2. What the omega value controls is how fast you oscillate. If I up the omega value to 4, I will oscillate quicker. Basically, your particle, if it has a low omega value, it goes nice and slow. If you give it a large omega value, you're basically looking at a much quicker oscillation. Does that make sense? Okay, the next thing. Do you start from the start or do you start from the middle? Okay, if you're starting from here, you're neutral, which means you're in a sine position when t equals 0. If you start off at an extreme, which is either side here, so if you start off at a positive extreme, so this is the equilibrium position, and we're saying that positive x is in this direction and negative x is in the left direction. If you're starting off in a position of positive x, where do you start? Up here, 1 away. Now, going back to this equation here, the number that comes in front of the cos wave is your amplitude. In this question here, it's a 1. So basically, at any given point, your amplitude can be 1 meter away from your equilibrium position. So, as an example, if I'm at this extreme here, I'm 1 meter away. If I'm in this position here, I'm minus 1 meters away, a displacement of minus 1 away from the equilibrium position. We're talking about we'll take starting from the middle, okay? When we're talking about starting from the middle, we're talking about sine functions, okay? And we're going to examine the effect of omega on sine omega t, okay? So please remember your x value, there's two of them drawn here. One of them is sine 2t, and the other one drawn is x equals sine t. Okay, so they're the two drawings we drew there, okay? So, first of all, using these two here, which one is which? Which one's 2t and which one is t? Sorry? The blue one is 2t and the other one? T. Now, can we take it, this box of information here? Everybody see where I'm confining the box to? I'm confining it from 0 to 3.1. Okay? I'm confining it to what am I doing? I'm confining it to the periodic time. Okay? Or sorry, I'm combining it to just 3.pi seconds. Okay? So what I want to say here is that this one here, the blue one, it starts in the middle, it hits one amplitude, it goes back to the center, and then it hits its second amplitude, and then returns back to its center. Do you understand? First amplitude, second amplitude, returns back to where it started. What's that called? There's a word for it. period. It's the time it took for it to complete a complete oscillation is what's referred to as the period. Okay? Does the red one complete a full period in the same time frame? What does it do? It goes to the right and then stops right back at the center because it's stuck here, and then it's going to take another pi seconds for it to go back here and then back to the center where it came from. Long story short, by having a 2 instead of a 1, you double the amount of oscillations. You half the periodic time. Do you understand that? Likewise, on the next slide, if you have sine, we'll fix this once again to 2 sine 2t, or sorry, sine 4t, and x equals 2 sine t. First of all, what's the amplitude of this motion? The amplitude is 2. How many oscillations, let's say, which one has more oscillations? Sine 4t. What sine 4t does, 4t does this in pi seconds. We'll stop pi seconds is once again here. Okay? Sine 4t, what it does is, it undergoes it hits the peak once, we're here, goes back to center, we're here, goes under, then back to center, back up, back down, and then back to the center. How many full oscillations did it complete? 2 full oscillations. The other one, once again, as like last time, only completes half an oscillation. This one completes half an oscillation in pi seconds, while this one completes 2 full oscillations. Okay? Hence, the periodic time, the time taken to complete 1 full oscillation, is 2 pi over omega. When omega equals 4, your periodic time is going to be pi over 2, roughly 1.6 seconds. When your omega value is 1, what's going to happen is you're going to get t equals 2 pi. 2 pi is roughly 6.28 seconds. So that pi is only 3.14. Hence, it's only completed half an oscillation. Would everybody be happy with that? Now, this is great for sine and cosine waves, where you either start off in the middle or you start off at the very end. What happens if the start of your question is in between? Okay? That's where the real skill comes in handy. Let me show you another example. What I have here is, once again, I'm going to stay with x equals sine omega t plus alpha. Okay? And I have two new equations. The 2 equations I'm going to use are x equals 3 sine t, or x equals 3 sine t plus 0.6. Okay? Now, what happens next, guys? This is straight from your notes. Which one is which? Which one is which? Blue one is red one, or the orange one is this one here, and then the blue one is this one here. Now, what happens is, in the blue one, in the red one, where do we start? We start dead center, don't we? So we start here. In the second one, which is the blue one, where do we start? It's the same amplitude, isn't it? Yeah. We did start here in the last one, but where are we going to start this one? About 1.6, I'd say, yeah? 1.6? Can't be sure. Actually, just 1 second, guys. Just want to make sure that isn't 1.6 on the money. The 0.6 basically shifts the axis 0.6 to the right. So, or sorry, 0.6 to the left. It shifts it so that you're no longer starting at the center, you're starting at a different value. So this question here would be, you're starting roughly 1.6 meters away and you're heading away from the center. Do you understand? You're heading away from the center. Is that okay? Therefore, when we because the new location is a positive value of displacement, a positive x, this means that your new starting off position is positive 1.6 meters away from your old position of equilibrium. Is that okay? Look at cos being affected as well. X equals 2 cos t. X equals cos t plus 0.6. Okay? Now, what happens this time is we have a a black one, is it? This is the black one, and the other one is the green one. Okay. Now, once again, this one here is starting off at a positive 2 meters away from equilibrium. It starts off at the extreme value. Everybody alright with that? 2 meters away. The other one, however, has been 0.6 has been added onto it. So it's actually starting off lower. Because what's the only position? You have to, basically you're starting off lower. So, quick question. Are you heading back towards equilibrium, or are you heading to the right or to the left? Look at the graph. Are you going towards 0 or are you going away from 0? Sorry? Towards. So here's something very interesting for you. Cos is towards 0. And in the last question, sine was, anybody? Away. Sine away, cos towards. Everybody alright with that? Sine away, cos towards. That leads us to our question. Okay? Sine is away, cos is towards. Alright. With this in mind, we're going to read this question. A particle is performing simple harmonic motion of amplitude 0.8 about a fixed point 0. A and B are 2 points on the path such that OA is 0.6 meters. So, if you draw your diagram, okay, you're not starting here, that's the position of equilibrium. A positive 0.8, or sorry, a positive 0.6 will leave you here. And then a positive 0.4 will leave you here. Now, first question. Which one do we hit first? The 0.6 or the 0.4? What's the language of the question saying? Travel from A to B. Are we going away from the center or towards the center? Towards. You're using a cosine function. Okay? So, save that one for later. You'll see that in a minute. That's some good stuff there as well. Now, what we're going to do is this. In our notes, it says x equals a sine omega t plus alpha. That's great if you're going away from the center of the circle, or if you're going away from the center of oscillation. You've determined that you're going towards the center of oscillation. Change that formula into x equals a cos omega t plus alpha. Is that alright? Now, next thing you're going to do. When does t equal 0? When does t equal 0, guys? When it's 0.6. It says it takes 2 seconds. It takes 2 seconds to go from A to B. We're going to set A as our t equals 0. So, 0.6 equals 0.8 cos. When t is 0, guys, we don't need to know that omega value. It's just going to be cos alpha. Divide 0.8 over. Cos alpha is going to equal 0.6 over 0.8. Cos inverse that, what do you get? When you cos inverse it, you're going to get you're going to cos inverse 0.75, and when you cos inverse 0.75, you're going to get an alpha value, or a correction of 0.7227. What this 0.7227 does is quite obvious. We should be starting off at 0.8 by traditional sense. Because we fixed the t value, because we fixed t equals 0 at 0.6, this correction basically shifts your wave either left or right to make the correction that you're actually going to be starting off the question 0.6 away as opposed to 0.8 away. Yes, Tom? We have two different times, so now we know that the alpha variable is 0.7227. This means the equation we're looking at now, remember the whole point of the question is to find out the periodic time of motion. If you're looking for the periodic time of motion, you're looking at t equals 2 pi over omega. Our whole goal of the question is to find out the omega value. If we find out the omega value, we find out the answer to the question. Right? So that's how you'd find out exactly what you're looking for, and that's how you'd come to the conclusion that you need omega t in your equation. And you have two different displacements, which are two different x values. You need to relate a x displacement to omega using a time variable. That's your choice. Okay? Now, what you're going to do next, guys, is when t equals 2. When t equals 2, the x value is 0.4. 0.4 equals 0.8 cos omega t, but we have our correction, which is 0.7227. Is that right? The correction is the same. Now, can anybody divide across by 0.8 and you get a half? Cos omega t. Oh, sorry, what's the t value? We have a t value as well, don't we? So it's 2 omega plus 0.7227. Now, what we're going to do next is cos inverse a half, and we get a pi over. Is it pi over 3? Huh? Sorry guys, what's cos inverse a half? I'm just drawing a mind blank. In radians. Huh? Okay. Cos inverse a half. Pi over 3. Now here's what I want us to do next. Pi over 3, take away our minus 0.7227 equals 2 omega. Okay? And then divide it by 2. I have the answer here. Omega is going to equal 0.16225. Is that alright? 0.16225. Now, you obviously don't. Your question's near enough done now. All you have to do next is your periodic time is 2 pi over omega, which is going to be 2 pi divided by your 0.16225. Your periodic time is going to be 38.73 seconds. Okay. Stop here for a minute. What we're going to get next here, guys, is this. I've actually answered the question for part 1, but I'd just like to go one step further. The step I'd like to introduce you to is this. If I write down this here, it's 0.8 cos, it's 0.16225 t plus my my alteration of 0.7, my alpha value of 0.7227. Now, everybody cool with that? So, what happens is this. over 6 seconds, or sorry, over 2 seconds, see the gap of 2 here? If I draw this function out, what happens in the first 2 seconds? I go from 0.6 meters away from displacement to 0.4 meters away to displacement, yeah? And you can see it's a relatively slow lumbering oscillation, yeah? It's a slow oscillation. Its periodic time is over 38 seconds. It's very slow. So, as an example, we're literally talking this type of speed. We're literally talking, we started around 0.6 away from the center, and you're just literally crawling along. And you're taking all day to go from here, and then you're going to go all the way back. You get the gist of what I'm saying. Now, there's a second question, and this shows you, this mimics this pattern your wave function does. Now, there's a second question, and in the second question, instead of it being 2 values, this time it's 0.6 to the right, followed by 0.4 to the left. Now, Killian made a very valid point. Killian's point was that initially it's going towards, and then it's going away. Do you use sine or cos? It's what it's initially doing is what's relevant. It's initially going towards the center, cos towards, sine away. Okay? So because it's going towards, now, what do you think? In the last question, it took 2 seconds to travel 0.2 meters. In this question, it took 2 seconds to travel a full meter. Which one's moving faster? Scenario A or scenario B? Scenario B is going a hell of a lot faster. What, in this function, what controls how fast it moves? The omega value, thank you. The omega value is what's going to change. So the omega value from the old part is now irrelevant. There's a new omega part. Hence, there's a different periodic time. This time is going to be a hell of a lot shorter than the old time. So, we go straight back to our cos function. We don't have to do the original one again because, sorry, one sec guys. X equals A cos omega t plus alpha. Now remember at t equals 0, x equals 0.6, yeah? We already did that in the last question. The alpha value turns out to be 0.7227. Here's the hard part. What's 0.4 out the other side? What's minus 0.4 equals an amplitude of 0.8 times the cosine function times your new omega value you don't know, yeah? What's the time? 2 seconds like last time. So 2 seconds, 2 omega. Your alteration, your 0.7227. Bring it over. It's minus a half cos 2 omega plus 0.7227. Alright, cos inverse that, and what do you get? Now remember, time is positive, so you have to take the next one up. Which quadrant will it be in? A, S, T, C. It's going to be between pi over 2 and pi. You have to take the next value up. You can't take the negative angle because time is positive. Okay? So what we're going to do is we're going to cos inverse minus a half, and what you get? Anybody? Was it? Minus pi over 3, is it? So it would be minus pi over 3, but we're talking about the second quadrant. Second quadrant is 180 minus r, which is basically pi minus pi over 3, which is 2 pi over 3. This 2 pi over 3 equals our 2 omega plus 0.7227. Bring the 2, take away the 0.7227 away from 2 pi over 3, and what you're going to get is 2 omega equals 1.3717. Then you're going to divide that and you're going to get a omega value of 0.68585. It's a larger omega value than last time, hence more oscillations as opposed to slower oscillations expected from part 1. Let me wrap it up. And then finally, 2 pi over omega is your periodic time. 2 pi divided by 0.68585. Your periodic time. Make a prediction. Bigger than 38 or smaller than 38? A hell of a lot smaller than 38 at 9.16 seconds. That's seconds. Okay, Tuck. He's asked me about basically with this periodic function. I'm just going to draw a rough. We start up there, but we're oscillating a bit quicker this time. Okay, just assume it's a symmetrical looking curve as opposed to what I just drew. Okay, now what I'm going to argue what is this. He says, well, look, that's a 0.4 there. That's a minus 0.4 there. He asked me why do I need to take the second quadrant on as opposed to the third quadrant, right? So ASTC, simple harmonic motion, is based very close to the math is based on circular motion, believe it or not. Okay, so ASTC. Now you hit your 0.4 here. You go down. Cos now becomes negative. Would you agree with that? The cos was negative. It was a negative 0.5. Okay, and this value is the value we got in the second quadrant. It also hits minus 0.4 shortly afterwards. Again, if you use the third quadrant, that would be when it's on its way back, hitting 0.4 again. So drawing this by diagram, you'd start up here at 0.6. You'd hit your center would be here. You'd hit your plus 0.4 here. You'd hit minus 0.4 for the first time here. And then when you come back, you're here. And then when you're on your way back, you'd hit it again. And if you got the third quadrant answer, you'd be getting this time here as opposed to this time here.